Okay, cool. So the agenda for today's tutorial consists of three main parts, so to say. Let's arrange them one by one. Okay, so the first thing, first of all, we will talk a bit about training and testing and validation splits. Okay, splits and their curves. Okay, and how do we interpret these curves? This is the first thing on our agenda. The second thing is we will continue with the lab that where we left the last time. You might remember that last time we were in the middle of implementing logistic regression ourselves. So this is what we will do: implement logistic regression manually. And the third thing will be we will talk about the assignment number two. So that's all what we will discuss in today's tutorial. So let's start with the first thing that is a more theoretical one, so to say. And so you might remember that Professor Kleinschreiber asked you guys to go through a brief history of neural networks and deep learning. And so I'm hoping that you guys have already maybe gone through that briefly, but nonetheless, we will cover what we need to cover in today's tutorial. So you might remember from the last time also that usually in the field of neural networks, there is a concept of training epochs, so to say. So what happens is, let's say we have a data set D that consists of x1, y1 up till xn, yn. So we have n samples in our data set, and we want to learn the model, the features of the neural network. We want to learn the weights of the neural network such that uh, for the input x, the model is able to predict the output y. This is the main task, because in the end, in a nutshell, our neural network is just a fancy function. So, just a moment. Okay, so this is the main idea that we have at our hand. And what happens is, more often than not, you iterate over these samples and again, because usually one run of the whole algorithm through all the samples is not enough to train all the weights. So we run this again and again, maybe I don't know, so for sometimes like for 100 epochs, maybe 1,000 epochs, depending upon the model, until a convergence criteria is achieved. These things might be abstract to some of you guys right now, but they will open up as we go along. So what happens is, there are multiple problems that we face on the way. For instance, first thing is this: usually neural nets need a lot of data to train, and when we say a lot of data, we mean that this n can be really huge, maybe in millions, so to say. So if we feed all this data to neural net in one go, like if here we feed all the data set, of course neural net um, uh, will try to, like, it will work with this case also, but it will need a lot of memory. The neural net will and this architecture will need a lot of memory to learn anything from the whole data set. So what we do is, in that case, we divide the data set in smaller chunks. So instead of this the set of n elements, we say that we say that our data set consists of d1 till, let's say, uh, dtr. Like this is for training just, and every D then consists of, let's say, x of I1 till x of I1, y of I1, and it goes to x of I, it goes to x of k, or x of M1 and y of M1, where M1 is the size that we choose for these smaller data sets. and the same partition follows throughout the this set d1 to dtr. So this is how we split our training data set in smaller chunks, and what we do is we feed this smaller chunk for every training epoch or every training iteration. Okay, now this concept of iterations might be becoming more clearer to you, because now if we only run this once, of course we won't be able to get we won't be able to like the neural net won't be able to look at the whole data. So we at least we need to look at this tr this whole data set. This is tr trainings. Okay, this is one motivation, and the other motivation of course comes from back propagation, where we know that back propagation actually is not like does not converge in one iteration, so to say, in one go. It needs multiple attempts. So for instance, if this is our function and this is the local minima, the stochastic gradient descent will move something like that, and depending upon the cases, it might not even converge to a simple point, but maybe just move around the point like that. But you can see like this is one iteration, second, third, fourth, fifth, sixth. So with every iteration it comes closer to the minima, so we need more than one iterations. So this is from where the concept of iteration comes. So now we have had a look at the motivation of splitting the data set, because of course we want to avoid to feed the whole data set in one go. And the second thing, we have had a look at the motivation for iterations. This comes from this back propagation that we are using. So now that we have discussed these two things, now we move on and we have a look at what we say bias and variance trade-off. So what do we mean by that? What happens is, let's not talk specifically in terms of a neural network. Let's talk in terms of general models. Okay. So suppose we have a simple model that is a linear curve or a line, so to say, which is like y is equal to mx plus c. Okay. And we need to fit this line to our training data. So here we have two parameters to be learned. One is m and the other is c. So our data might look something like, this is our data, and we like the best case will be to learn something like that, right? That represents the whole data as good as it can. So you see, what happened is we were given a data. These points are the data samples of the data. We were given the data, and what we did, we assumed that this output relation and the input and output follow a linear relation. This is our assumption that we made, right? And these are the types of assumptions that we always make when we define our model. So when we go to, okay, let's move on, like yeah, let's see another case. We might have a case where we have y is equal to ax square plus bx plus c. This is the equation of like a 2-degree polynomial, and here we have three parameters to learn, right? And in that case, in fact, suppose in fact we can maybe modify this example to uh, serve our purpose. Suppose this is our data set, right? And the linear line that fitted this the linear line that fitted this data set was something like that, right? This is the linear case, and the polynomial, the 2D polynomial will be something like that, right? This is quadratic case. So what happens is, you see, based upon the assumption that we made about our model, we had different relation, like we had different results, so to say. Here we can visually see that the quadratic case was serving us better compared to the linear case, because our data was probably something like quadratic with noise added to it. So if we keep building upon that, we reach to a point where we have a neural network where we have maybe millions of parameters, and we like based upon the number of parameters, our model might predict one thing or another. So based upon the number of layers and how these layers are stacked and things like that, these all things make our model, make the model of our function. Right now, this is the model of our function. And in neural net, we have this complex model with linear layers and activation functions and whatnot. So this is these are the assumptions, so to say, that we make about our model. And when we simplify these assumptions, this results in the bias of the model, right? So for instance, here our assumption, this quadratic, when we say that okay, the relationship is quadratic, this is one assumption. But when we say it is linear, we have simplified our assumption. You see, we have decreased the number of parameters to be trained, to be learned by the model. So when we make an assumption simpler, it generates bias in the model, right? So and now suppose another case where our assumption was that we want to learn, I don't know, let's say like 10-degree polynomial. In that case, we might have learned something like that. So you see, this, I mean, let's say this is a 10-degree polynomial, right? So this is, maybe this is defining our data set the best, in the best way, like better than quadratic case and linear case. So if we see the, let's say if we see the differences between Euclidean distances between the estimated y and the actual y, we can see that this gives the least distance, and then this one, and in the end this one. So this one has the least bias, right? This one has moderate amount of bias, and this one has maximum amount of bias. This is the concept of bias. And the concept of variance in the data comes as a counterpart of this concept of bias. So what happens is, if we have a large number of parameters in our model, what happens is this model wants to, like, this model has now the ability to map, so to say, let's say in the best case, so to say, or in the extreme case, let's not say best, but in the extreme case, if we have a simple data set like this one, and if we have a large number of parameters to be trained, our neural net, our model will probably learn every mapping, you know. So in that case, our the distances between the predicted and the actual y will be zero, because we have predicted everything, so to say. But is this what we wanted? This is the other question that we need to answer. So right now, if we if we make use of the common sense, we can see that this quadratic model was probably the one that was explaining the data in the best possible way, and it was because it was also generalizing the our models in some way, right? And this maroon or this 10-day polynomial, this was this was very well mapping or very well learning the data set that it was provided with, but it was not generalizing well enough, because it is mapping very hardly, mapping very closely to the training data. So this this 10-day polynomial has least bias. This quadratic model has moderate bias, and I'm sorry, yeah, this 10-day polynomial has maximum variance, so to say, and this quadratic polynomial has a moderate variance, and this linear model has minimum variance. Variance you can see because of the way the outputs change based upon different inputs. Like this is in general the definition of variance. So let's plot them, these concepts, uh, to get an abstract feeling of what we have discussed till now. So what happens is, let's say this is the curve, this is the axis of model complexity. Okay, so the more the number of parameters, let's say the I mean, complexity can be defined in multiple ways, but let's right now stick to the case that model complexity refers to the case but that we have multiple parameters to be trained. And here we have and here we have the error that is outputted. So what happens is, if we have like when we increase the model complexity, the bias of the model decreases, right? This is what we have just discussed. So this is the bias, okay? And at the same time, when we increase the number of parameters, the variance increases, right? Because we have seen that here when we increase the number of parameters to 20 polynomial, we were able, like this this case, this maroon case with 20 polynomial has a lot of variance, right? The output is the predicted output is changing a lot with respect to the input. So this is the case that happens. And what we are looking, and if we accumulate these two things, if we accumulate these two errors, the resulting error is something like that, right? And what we want to do is, this is our variance, and from this graph we can see that there is a point somewhere in the middle where we have an optimal model complexity, right? This is the point of optimal model complexity. So here our model has, here the parameters of our model are not very large and not very small. They are moderate in a sense that the model has reasonable variance and reasonable bias. Okay, we have to live with both. If we increase one, the other decreases, and vice versa. So we have to find an optimal point where the model not only maps or not only learns the parameters based upon the training data, but also maps one well, or also generalizes well to the new or unseen data, right? Now to quantify this or to visualize this effect in during training, we use the concept of splits in the data set, right? We have already seen that one split is based upon the fact based upon the motivation that we cannot feed all the data set in one go to the neural net because of the memory problems. And instead we stick to the smaller chunks of the data set, which we call as mini batches, right? This was the one split that we talked about. Now there is another split in the data set, and that split, suppose this is our data set, this is our data set. What we do is we usually divide this data set in three parts. So let's say uh, these are the three parts where we have divided our data set. This one part is known as training split, so to say, or like this is the training data set. We can, like, this is actually the training split, but this is the training. This part is used for training, and this part is used for validation, and this part is used for testing. Okay, so whenever this is a way of visualizing this bias variance trade-off that we just talked about. So what we do is, this is only used during training. Okay, and when we train a data set, then we see how well it is generalizing to the unseen data. And this is a part of unseen data where we which we use as generalizing for, like, which we use for visualizing how well the model has generalized. And then this is the testing data, which we don't show usually during visualizing this bias variance. Instead, we simply, like, use this in the very end, so to say, to report. In fact, you will see in the in many of the papers that people only use training split and validation split. So yeah, validation split also has some other functions, like if we have some parameters that need to be tuned by hand, so to say, then we can use this validation split to to make a better, like, to find this point, to find this optimum point in a better way. So this is also a purpose served by validation. For instance, in case of k nearest neighbors, just an example, in case of k nearest neighbors, we don't know which k will be optimum for getting the least loss, or for optimizing the output. In that case, what we do is we can maybe take k is equal to 1 to, maybe let's say k is equal to 20, and we can see that for which value of k our model was predicting the training data set really good, and also the validation data set was also good, right? This is, I mean, just an example where K is a hyperparameter. There are multiple other hyperparameters, I mean, depending upon different models, and this is where this validation concept comes into play. So, and the other thing is, inside these splits, we further have these D1, D2, and up to DTR, right? These are the chunks or the mini batches. Okay, so these, let's say these mini batches are referring to the training split, and then similarly we have mini batches here for validation, mini batches here for testing. So this is how the two splits in the data set fuse together. So first, the bigger split is this training, validation, and testing split. And in every split, we have mini batches which we use for training or validation or testing. Now we come to okay. There is a question: does the error of training dataset and validation dataset tend to be the same if the algorithm good is okay? Yeah, this is exactly the point that now we are going to talk about. So the question is: does the error of training dataset and validation dataset tend to be the same if the algorithm is good? Now we will see uh, there are actually more than one factors affecting this, and this is what now we want to talk about. So let's say here we have training plus validation loss different scenarios. Okay, so we will see different scenarios and we will see how we interpret what's happening. So let's proceed. And so what happens is, this is the number of epochs or the number of iterations, or let's say we can simply put T, like the time. This time can refer to epochs or training iterations. We can implement, like interpret it in both ways depending upon the context. So here, suppose like when our model starts learning, of course, training loss is high, but as our model learns, training loss becomes less and less and less, and then there is a point where our training loss becomes, so to say, a bit constant, so to say, right? So I will represent training loss with black curve, and test validation loss with red curve in this lecture. I hope I will stick to this. Yeah, let's see. So this happens when our model is learning, and and now if we also plot the loss for validation case, it will be something like, so you see what's happening is, of course, because our model was trained on the training data set, the loss decreased relatively quickly for training data set. And this is because of the generalization of model, that the loss on unseen data set or the validation data set also decreased with time, right? And what we have drawn here is the best case. So what happens is, now we know that this is as good a loss, like this is as minimum a loss as we could have attained with the given models, with the given parameters, with the given model, right? It might be the case that if we increase the number of parameters to be trained, we might get something like, let's say, where training loss is this. I mean, how, okay, yeah, let's do it like that. So this is T. And if we increase the number of parameters in the model, it is quite possible that we end up with this case. So what's happening here is, we can see that here for the given model parameters, our like both training and test loss became same, but still they were, I mean, let's say this value, just for your understanding, this was around, let's say, 0.5. But here we can see they are really close to zero. So maybe this is zero point 0.1, let's say. So when we increased the model parameters, we uh, we were lucky enough that our training loss decreased, but also our validation loss decreased. And now if we increase the model parameters further, what is expected to happen is that our training loss will be probably become really close to zero. Okay. Something like that. But what happens is, in the same time, our validation loss will not decrease any further. So now we know that what happens here is that when we increase the more, are you following me? What happened, like this was the case, let's say, just as an example, where we had 1,000 model parameters to be trained, okay, and we saw that okay, both uh, training and validation loss are quite similar. So this means our model has generalized very well. But now we need to probe further if there is a possibility that if we add richness to the model, if we add complexity to the model, is it possible that training and validation loss decrease further, and both of them decrease? For that, we increase model complexity, and what happened is both training and test loss further decreased. And this means that we were really lucky here. And now we come to the next part. We say okay, maybe let's try our luck one more time, and we increase the model complexity a bit further. What happens is the training loss now becomes really close to zero, but the validation loss has not decreased. In fact, is it has like increased a bit, right? So this phenomena is known as overfitting. Okay, why? Because our model had so much complexity, our model has had so much degree of freedom, had so many parameters to be trained, that it sort of started pinpointing the training samples, so to say, or it started learning the training samples so well that it failed to generalize to the unseen data. So you see what happened is, this first case this first case was, if this first case was somewhere here where we had high bias, yeah, we had high bias and relatively low variance. This second case was here where we found an optimum point. And um, when we went to the third case, it was maybe somewhere here, right? I mean, just to show an example. So now our model has high variance because it has fitted the training data really well, but it has low generalization ability because of low bias. So this is the concept of overfitting. Okay, so there is a question: what is the difference between validation and test? Could you please say it again? So, okay, so what happens is, when we train a model, there is a concept that we need to see how well the model performs on the data that it has not seen. Okay, so this training data, of course, is the one on which the model is training. So here we are very clear. This training data will be fed to the model again and again, and the parameters of the model will be learned. There are some other, so to say, parameters that are not directly trained by the model, but that need to be chosen by, let's say, a human expert, right? Let's say, for instance, if we are talking about a gradient descent, what should be the rate of decay, or what should be the rate of update, or for the optimizer, like if we are adding the gradient, how it should be added, like there are different multiple hyperparameters. Even in a simpler case, the number of layers of a neural network, right, and the number of parameters in every layer. These are the parameters that are not, of course, optimized by the neural network, but here a human intervention is needed to optimize them, right? So what we do is, we have a look at these two curves, training and validation curves, to find out which assembly of these hyperparameters sets the best. Okay, and the way we do it is, we compare the training loss with the validation loss. And remember, right till now we have not used this part of data, this test data, we have not used this data at all. Okay, once we know, okay, this data was continuously fed to the model, and this validation data was used for fine tuning the hyperparameters. Only then, afterwards, in the very end, we'd run this model on the test data set and we say, okay, this was the test accuracy. So another question is, does the result on the validation set also influence the parameters, or it is only to evaluate the new trained parameters? I mean, it depends. It depends upon the model. But let's say if we talk about the neural network, and I don't know if you guys have gone through that a brief history of neural networks web page. But what happens is, suppose in the case of neural network, there is a parameter called learning rate. Okay, so this means like when we have a loss function and then we calculate a gradient, the learning rate defines with what speed the parameters should be updated, right? So sometimes what happens is we say, okay, let's say if like a unit, if a parameter is, I don't know, let's say h parameter should be updated by h new, like h new is equal to 1 minus lambda into h old plus lambda into delta. This is a gradient, right? So if this is, let's say this is around 0.001, right? So this is a hyperparameter that is not learned by the model. So this is what we are what we are doing here is we are defining that how the parameter, how the with which speed, with what speed the parameters should update, right? So this is like a hyperparameter that we need to tune ourselves. This will not be trained by the model. This we need to tune ourselves, and to do that, to see that which value of lambda will suit the best. For this purpose, we have a look, we check these curves, and then we decide that okay, for this value our results are the best, so we will stick with this value, and we will only hope that on the test data set the results are also similar to the one on the validation data set, because the validation data set was not actually fed for training. Like it was used by the human expert for judgment of this bias and variance trade-off. So now we have seen the concept of overfitting. So right here we can say, I mean, this is okay. Let's see. This is one way of saying underfitting, but okay, let's see. So this there is an opposite concept to overfitting, and that is called underfitting. So what happens is, this is our training data set, and this is our this was our training loss, the black curve, and the red one is our test loss, validation loss. So you can see that both the curves are decreasing, and both have probably reached as like a, a constant value, so to say, like a plateau, so to say. But there is a gap between the training results and the test results, right? So this gap means that the model is has underfitted. So we need to maybe increase the number of parameters. We need to increase the model complexity so that it has the ability to generalize well to the new data also. And yeah, so now we have seen the case of overfitting and the case of underfitting. Okay, let me ask you guys another case. Suppose this is the training loss, and uh, just a moment. Uh-huh. Maybe this, yeah. And this is the validation loss. So, what do you suggest here? What do you diagnose here? Like, if what do we need to do now? Like, what if you were the human expert, and these were the two results that you get on training for training data set and validation data set? What would you do here? Maybe make it a bit more clearer. Yeah, maybe this is better. Exactly. So there is an answer by Julius, in fact, and also by Mortis. Like two people have answered this correctly. This means that we are in a good region, but we have stopped it prematurely, so to say. We need to train this further. It seems that the loss was decreasing. It had not reached a plateau. It had not reached, so to say, something like that, right? So as long as our loss, both like training and test losses, are decreasing, we don't need to stop training. Okay, we need to we should train further, and we should see that we should train further until the time we get something like this, right? So in this case we will say train longer. Okay. And is there anything else that is left? Let me think. Mm, so okay, let's have a look at another case. Suppose this is our training loss, and this is our validation loss. So what do you what do you infer now? Like if you were the human expert and you found the curves like that, like what would you decide then? Like, okay, so yeah, so what happens here is this is actually a fishy case, so to say. This case is something that shows that probably there is something wrong with the split, so to say, because this should not happen. Like in the best case, in the optimal case, or if everything is done right, this should not happen, right? So what happens is, um, l- uh, let me give you an example. Suppose our data set consists of two classes, right? This is like these are the two classes, right? And just by coincidence, what happens is, okay, or in fact, let's be even more clear. So let's say our data set has these two classes. So one is a big class and one class is really small, right? So when we make a trainings and test validation and test split, what we do is, like in the validation split, we have only, let's say, one element from because when we do this split in the relatively same ratios, we have only one element from a validation class, and we have, let's say, this much elements from we have only one element from class C1, and we have this many elements from class C2, and the rest are for training. Let's say, let's forget test for now. So what happens is, maybe our model by luck, okay, by luck, maybe our model learned a bit, because this was a big class. Of course our model was probably a bit biased towards this class. If we did not take manually, if we did not take care of this bias, our model will be probably biased towards this other class. And maybe our model learned to distinguish this class, because maybe this was the boundary point. Let's say our model had a cutoff here, so this is all C1, this is all C2, and the one element that we added in the validation set was recognized well by the model. In that case, our training results are poor, but our validation results are very, very good. Why? Because our validation data set is not the true representative of our test data set, right? So we need to redefine our validation data set. Okay. It is like, it is a common sense thing, that if, because this training data set is the one that is actually fed to the model, and the model actually tried its best to train on this data set, and even then it could not achieve a loss lower than this value. But the validation data set that was not even shown during training, that achieved better results. This is simply not possible if everything is done right. So this means that the split was wrong, or the validation data set is not a true representative of the training data set, right? So if you are like, this is a good case, because it says, okay, you are going good, just train a bit further. This we already see, we can try with increasing the model complexity. This we know that, okay, now we are maybe in a bad region, we need to go a bit back and decrease the model, or maybe add regularization or decrease model complexity in one way or another. And this is the best case that we need to um, land upon if we are training our model for the models that need epochs or that need time for training. So this was some basic like test cases for diagnosing how how the models behave, and how the training and validation losses behave. You know, in practice there are many funny things actually happening. This is, in practice, is not a piece of cake like we discussed now. You might see something like the case that your training model started like the loss started decreasing, then it became constant, and then it suddenly decreased. I mean, you find like every funny thing when you're training, and then you might also find that your loss was going good, it was training, and suddenly it blew, right? So to avoid these things, what we do is usually we save the parameters of our model after, let I don't know, every 10 epoch sets, let's say. Or another way is we keep on looking at the loss for keep on looking at the loss, and if our loss starts increasing for, let's say, 10, or let's say 20, I mean, this you can choose this, for, or 5, whatever, for 5 consecutive epochs, we say, okay, this is now we are going in a bad region, so we need to simply save these model parameters and report these parameters to our post. We don't show what happened after that. We only show the story till here, because this is the good part of the story. So yeah, we have everything happening here. And we need here we need to be clever as human beings to see how to get the best out of the model. I guess we have a let's say 5 6 minutes break here, and we will then proceed with with the lab solution, and resume with that. And afterwards, we will discuss the assignment and call it a day. Okay. Okay. So you might remember the last time we started with writing the logistic gradient function for that manually sort of derives the gradient of the logistic regression. We will just go through the task one very briefly for revision, and then we will proceed. So you might remember, actually this task one is coming from the last assignment. Like, this is the whole last assignment where we pre-processed our data, where we had like the reviews, and which they also contained HTML tags. So first we removed the HTML tags, then we removed everything that was not letters and numbers. Then we converted these resulting strings to lowercase. All the letters were converted to lowercase. Afterwards, the stop words, so to say, or the words that we have assumed that for this purpose, like for this model, we are not required, like in, the, all, like small words like that. These words were removed, and the meaningful words were retained, and then they were joined by a space to form the final string that was like the pre-processed string. Using this function, we loaded training data as well as testing data. And after that, we again, like, sort of just sort of populated the clean train reviews array with the pre-processed training reviews, and similarly clean test reviews array with the pre-processed test reviews. Then we used a count vectorizer. You might remember we had two types of vectorizer studied during the last lab. Anyways, we use here the count vectorizer, and this is the same assembly as in the last lab. I guess maybe this number of features was 50 there, and we have used 5,000. Maybe there is some small difference, but otherwise the assembly is the same. We use this vectorizer and fit the training data, and then once the training data has been is fitted, we use this model to get the transforms of both the training data as well as the test data. Okay, and then we remove these pre-processed review, like we empty out these variables for like to get free memory. And yeah, that is all. Then we convert these features to array. So we see the shape of the features. We have like 20,000 training samples with 5,000 dimensions each, as we mentioned here. And yeah, afterwards, we talked about how we define sigmoid. You might remember that depending upon whether x is greater than 0 or less than 0, we use like e power x over 1 plus e power x. So, okay, just a moment. Yeah, just to uh, refresh this. You might remember that we had two implementations of sigmoid. One was 1 over 1 plus e power minus x, and the other was e power x over 1 plus e power x. So depending if the if x was less than 0, this was more stable. If x was yeah, if x was greater than 0, this was more stable. If x was less than 0, this was more stable. So this is what we did here. And afterwards we calculated the gradient. And gradient, again, just to refresh this once again, you might remember from this PDF that also has been uploaded to the Moodle, that the gradient with respect to W is this term. And this is the same, you see, this is, if you forget yi for a moment, it is 1 over 1 plus e power this whole thing, right? In other words, it is the sigmoid of minus of this thing, right? So this is what we are doing here. We use this minus, and this is the same thing as this part is the same as this part, right? So yi into w transpose x plus b, and we don't of course use b specifically, because we will include b in the w vector to make the case homogeneous. You might remember we talked about this case the last time, that we only need to look at homogeneous case, and the non-homogeneous cases are dealt within this case. So and then we use this minus to make it like to make this sigmoid. And this minus like outside is this one. So then we are left with this yi and xi. Since we are using this matrix formation, we use a dot product of this x train to incorporate all of them in one go. And we multiply them with y. Here we have done this part, and then we multiply these two vectors, and it results in the summation. um, and afterwards we take an average. And this is because we are not feeding um, the summation of the loss function as we did here. Where actually we will see after in the next task that we are feeding here the average, like we divide by 1 over n here. So this is the loss function, but we use this, we average this over the number of samples and use that loss function. We can use this one, this is a sum loss, so to say, and we can also use its average form. It doesn't affect learning, so to say. And then we are using this 2 into regularization rate into w. So this, you might remember that we talked about this comes from here. You might remember that we say, like this sorry, this one, we said that we needed to add regularization to keep, like, to add that effect that we wanted to have norm minimum. You might remember all the discussion on these projections and minimum distance and unit norm and things like that that we had in the last uh, the lab before the last lab. So that's to, like, for adding a regularization, what we do is we add here like a norm of w square. As you can see here, lambda into norm of w square. This is lambda is one of the hyperparameters. You see, this is again a type of the hyperparameter that we would choose probably by looking at train and validation curves. Okay, this is one of those things. So because this is not tuned by the algorithm itself, we have to define this manually, and we have to see on which lambda our model learns the data set the best. So if we use, if we see gradient of this, it is 2 w, and that's why we end up with this 2 lambda into w, as we can see here, like 2 regularizer, like regularization weight into w. So this concludes the logistic gradient that we saw the last time. Now we come to the next part. Let's close this. The next part is find, like, you write a function find w that expects a training set matrix x train, a ground truth label vector y train, a step size alpha, and a maximum iteration number max it that determines The optimal logistic regression weight vector W star by performing gradient descent, that is calling logistic gradient in each iteration. Make sure to include the affine offset W not equal to B in your model. So now actually we need to sort of use this gradient logistic regression and this gradient function that we wrote, and we need to use them to learn the optimum or I mean the best W that fits. This is the model, right? This is the model parameters. The W is our model parameters. So this now we need to find this one. So what we do is first we like start with an placeholder arrays, so to say. So we have X offset, and we what we do is we don't like for the first like so if you see we have here increased by one. If we have added one, this plus one will take care of this um, um, so okay, let me show what we are doing here is. So what we are doing here is, so this is our X, and we we use it we add its dimension, we increase its dimension by one, so that in this last half we add X train, and in this first this will be used as our here we put one, because you might remember that we said that like we can use wx plus b is equal to the case where we have where we have w, or like something like w transpose and b into x and 1, right? Or we can also write X transpose if that's easy for you guys. Like, so we can also type X transpose and 1 and W and B, right? So you see this one, that's why we increase this dimension by 1, and we add this one um, in the first dimension. So that's why we initialize it with ones, and for all the like apart from the first row, all the rest is filled by X train. Okay, so this is in fact, let's yeah we can do this in the transpose form to see what's happening here. So now let's come back. So now we have taken care of this X. We have added this 1 to X, and now we will similarly we will initialize W with again with ones, and its shape is also the same as the shape of X offsets. Dot shape 0, like its shape will be so the number of dimensions of X plus 1, because here we added this plus 1 to increase the number of dimensions by 1. So now we have seen that we have also added W node equal to B. Right now, of course, it is initialized as 1, but we have now added, uh, now our W is P plus 1 dimensional if P is the dimension of X. So if after that, if we are provided with explicit initialization, like for instance, someone might say that, okay, I want to initialize W with random uh, Gaussian random noise or something like that. In that case, we explicitly initialize W with this part, and then we start with loss equals to minus equal to infinity. Of course we want to minimize the loss, so we start with the maximum loss possible, and then move down with every iteration. So ah man, I closed that, just give me 1 second. Yeah, this. So if you see, this is the loss function, right? So this zzz is calculating actually this loss function. If you see this 1 plus e of, we have also discussed that. So 1 plus e of all this, we can add a minus here, like just a moment. So like this loss is the same as adding like 1 to n. We can add, if we add a minus outside and a minus inside, like if a minus gets inside log, it becomes exponent, or in other words, we can do 1 over. So this is 1 over exponent of all this, and this is the sigmoid form, right? So this is what this is how we will be implementing this. So let's, okay. So you can see that's why what we are doing is, here again we are taking sigmoid of this part inside, like W transpose X, and we are of course not using B because it was already included inside W and X offsets. So we simply use dot and we multiply with this with Y, as we can see here. And afterwards we sum this loss as seen here, and we divide this by the number of samples. And this is what I was talking about when we used here average, because we are not using the sum, but we are using the average loss for training. But it does not affect it, like averaging sort of, you can say that maybe it is maybe numerically stable. Like if every sample is adding a loss of one, like in the very beginning the losses are a bit larger. So if every sample adds a loss of one, and if we have millions of samples, I mean it might not be numerically very feasible. I mean this might be one thing, but we can use summation as well as average, so it does not affect that much. Anyways, so we use this loss, and after that we use this regularization, like lambda into norm of W square, as we saw here. And of course, B is not required because it is already inside W. So after that, what we do is we iterate over the given number of epochs, and for every epoch, this loss was calculated, and after that what we do is we do random permutation of the input X. And the reason we do this is, the main reason we do this is because we have implemented this function in the batch, in the mini batch form, so to say. So uh, again, if you have a look here, we want to add we want to enhance the generalization ability of our model. So one of the tricks that works really well is, so if we have this data for training, and these are the so to say mini batches, right? We don't always feed the same um, like the same mini batch for every training. In fact, what we do is we shuffle the data so that we have like this shuffle data. And now we use this. Now you see, this batch might have elements from here, from here, from here, like from different points. So this shuffling actually adds the sense of randomness, and it avoids the model to like sort of fixate on the indices, so to say, or fixate that okay, first mini batch always appears from, let's say, the class number one or class number two, so I will always like it sort of it avoids it adds generalization to the model, so to say. That's why what we do is we are given the number of mini batches, and we find out like the question. Let's say if we had 1,000 samples, right? We have 20,000 samples, right? We have 20,000 samples, and number of mini batches is 100. So we have like 200 mini batches to work with. So this what happens is, here we here we feed the mini batch um, like and here we feed the permuted, from the permuted version of our offsets. You see, we use the permuted version, like we use the iteration for them, like for example, this first part is picking up from 0 to 100 if we have 100 on the set of the size of mini batch. In the next iteration it will pick from 100 to 200. But what happens when we calculate the permuted indices, it is not from 100 to 200. It will be random indices from X offset. So that's how we are dealing with this. We are adding this randomness in the mini batches. So what, and again, you can also see that now we have divided our data set to in mini batches. So in every iteration, we only need to like the memory that is needed by this algorithm is only only scales with the number of mini batches, not with n, so to say. So that's why it is also memory memory friendly, so to say. And so what we do is we have calculated the loss, and then use this logistic gradient function to minimize to find the gradient. And afterwards um, we that is like to find the new to find the new delta, to find the gradient, and then that is subtracted from uh, w. And um this is how we keep on doing for all the epochs, and for every epochs we keep on doing for all the mini batches. And once the number of epochs is finished, we say, okay, this is what we came up with, and we return this. So this is all what's happening here. And in fact, a part of this function also covers the third, the C um task that we have at hand in the assignment, in the tutorial. The C part says the data set at hand is quite large. Applying standard gradient descent could likely lead to Python throwing a memory error exception. To avoid this, we will employ a variation of stochastic gradient descent that has been proven successful in training deep neural networks. In mini batch learning, each iteration of algorithm is replaced by a so-called epoch. In each epoch, the training set is divided randomly into subsets of equal size, the mini batches. For each mini batch, the gradient is computed and applied only with respect to the samples of the mini batch. An epoch is finished when the gradient step was performed for each mini batch. So you see, like this epoch is finished when we have applied this gradient for all the mini batches. So we right now we have not written this simpler form of find w, but we have already included this more elegant form where which was asked here. So modified find w such that it is capable of mini batch learning. You will need to replace max iteration by number of epochs and add the parameter n mini batch to your function definition, and take care of normalization of the gradient and the loss function. You see, now you can see that this averaging is coming really handy. And yeah, so this part C is already been discussed here. And now this, when this has been done, now we go to the actual fun stuff where we implement this thing. Write a function classify log that expects a weight vector w and the test set matrix x test, and classify the samples in x test via logistic regression, returning a label vector y test. So we are given a x test, and we are given our a vector w, and we used this sigmoid to find the y test, and then test your implementation to find w and classify log on training dataset, and test dataset features with 10 epochs mini batches of 100 size, and step size of alpha equals 1. So now we have defined this function, but what this is doing is we have an x test, and we simply find the sigmoid, so like we have here x transpose w, and we are adding w naught. W naught was the first was the first element of w. We can also do it in the other way by adding ones as the first row to x test, and then taking a simple dot product and sigmoid. Sigmoid is simply used to like map the data between 0 and 1, and then we return the y test, because our answers are either 0 or 1. So that's why we use sigmoid. And now, based upon the threshold, whether the values are greater than 0.5 or not, we can decide if the sentiment is positive or negative. So now we test all of the implementation. So we have sentiment dot this like we get y train and y test, and w is obtained by running uh, this this function find w for 10 epochs, right? And we give them the x train matrix, and we give them y train matrix. And what we are doing here is we are simply converting 0 and 1 to -1 and -1, -1 to 1. So if y train is 0, 0 minus 0.5 multiplied by 2 will be -1. If y train is 1, 1 minus 0.5 is equal to 0.5, again multiplied by 2 equals 1. So this is mapping 0 to 1. This maps 0 and 1 to -1 and -1 and 1. and afterwards we give alpha and we give okay, yeah, maybe we have need to have a look at that. So after that we give number of mini batches, regularization function, and w of init is not given anyways. Yeah, so we call this function, and this these are the results. We can see that as the epochs, as we go further down the epochs, this loss keeps on decreasing. And once we find this, we use this function classify log to find the predicted y, and we simply use area under curve to find out how good we have performed. So right now we have already the area under curve is 0.92, which is pretty good, I would say. And we have a question regarding the mini batches. Yes, please type that question and I will continue and maybe answer when I see the question. So now moving forward to the part E, logistic regression is prone to overfitting. Like, I mean, based upon the number of parameters, we of course can overfit, and to prevent this, we use this regularization. You can see that uh, till now we did not use the regularization actually, but here we will use a regularization with weight 10 raised to power 10 raised to power minus 3 as asked in the task E. So we will run again exactly the same thing, like exactly these three things, like these three lines. Just the only addition is that now we are adding a regularization weight, and I have just copied the function definition above so that we see what's happening. So we are giving x train, this is y train, and the alpha is 1, number of epochs is 20, and number of mini batches is 100, and regularization is now transfer minus 3. Before it was not given, so the default value, that is 0, was used by the algorithm, so there was no regularization. When we add regularization, we can see that our results are better on test dataset. So you see, before they were 92 and now they are around 93, like 0.9349, about 935. So this concludes our tutorial. And the question is, when I ran the gradient function without mini batches, no memory error occurred. However, I was not able to exceed 75% accuracy despite using the exact same function for both, with the only difference being the number of epochs and batches. Okay, so Mortis, you see, the thing is actually there is um, only when I increase the numbers to like 1,000 iterations over the entire set came closer to 90. No, it should not be like that, honest. Because the thing is, if we have all the data in one go, the gradient descent algorithm actually sort of, how to say, it converges actually faster. But you see, there are actually a lot of subtleties involved. So we actually need to probe into that a bit further. For instance, if you see here alpha is equal to 1, right? Where was alpha? This alpha, we have given this alpha is equal to 1 in both cases. So this might be some, let me see, where is this used? Yeah. So we multiply this whole gradient with alpha. This is one is really really large. Maybe that's why it finds harder to converge. Maybe if we use smaller alpha, it will take more number of epochs, but it will converge to a better point. So I mean, there are a lot of subtleties involved. So, but it should not be like that. Like the mini batch case usually. I mean, if we feed the whole data, it actually converges faster. Okay, so it's like because if we have all the data, so we, I guess I already showed something similar, but so the thing is, if we have all the data and if we are lying here, we know that we need to, and if suppose if this is the path of if this is the path to sorry, if this is the path to minimize to reach the global to reach the minimum. If we are here, stochastic gradient descent will rigorously follow this path because we have all the data available. It will be like that with every iteration. It will reach this very quickly. If we have a stochastic gradient descent, like if we are using only one sample per time, it will not go like that. It will be probably going something like that, with every iteration, here. So it will go something like that, and it is very rare that it will actually land on the exact point. It will keep on revolving in the same neighborhood, but it won't land on the exact point. If we use mini batches, they are sort of a good compromise between the two, so they will be like something like that. And yeah, they will be something like that. So you can see that using all the data actually should be better. So if you did not get this memory error, maybe because your laptop had more memory or something like that. But if you did not exceed 75% accuracy, this intuitively this should not be the case. There are maybe there are other hyperparameters that you might need to look at, as I mentioned, like alpha, but this should not be the case. So we are only left with 10 minutes, and we need to discuss the last thing, that is the second assignment. So I hope you guys have submitted the first assignment, and you guys are done with that. So the second assignment is actually related to PCA, and I will go through this very quickly because we have like 10 minutes. So what happens is we have an X, and uh, so it is a centered matrix. So right now we don't need to worry about subtracting the mean and things like that. And we know that this is SVD sort of SVD representation, and we have assumed that SVD values are sorted in descending order. So this is the biggest one, and then this is the smallest one. So we want to the first task is we want to find a vector S such that this is maximized. So this is very simple. We need to find a normal vector S such that this result is maximum, and of course it should be like it should have norm equal to 1. The second task is that empirical variance of the inner products with the normalized vector A should be maximized. So please remember this. If you first please solve this one, and then you will have an idea about this one. So here we want to find out this a like here we want to prove that if A is set to the first column of U, right, the loading first column of the loading matrix, in that case this like the dot product or the similarity of A into xi is maximized. So this is something that you need to show. And here we have also a hint that write A as a linear combination of columns and verify that such representation does not affect the norm constraint. So this is the first assignment, and it is like more. It is to be done on, so to say, with paper. Or I would but recommend you to use LaTeX, as we have already given the instructions for the first assignment. And please don't give a screenshot of the proof or anything like that. So the task 2 says download the modified version of Yale Face database B provided on Moodle. This assignment has already been uploaded to Moodle, and it consists of it is just a description of the data set. It has 10 subjects, and each subject has different variations depending upon different poses and illuminations. So we have four uh, we have five subsets of this data set, and we will use only one subset, that is the subset number 0. We will use this subset as a training subset, and all the four will be used as test subset. So in the subset 0, the subject is illuminated by an almost frontal light phase. The other subsets have lights gradually moving from along the horizon. So we will use subset 0 as training and the rest for testing. So the first thing what we want to do is we want to write a function that, so when we say vectorized images, like we have an image, let's say, I guess it is 50 by 50. So we simply flatten this image, and it is a vectorized form of the image. So if we need, first thing is to write a function that if we have a vectorized image, like the matrix of vectorized images of the subset 0, and we want to find its SVD, only then of course we will have this U matrix, and this U matrix will then be from this U matrix we will simply pluck out the first 10 columns, and this will be the first 10 basis vectors that we will be using. Or I mean, I should not say basis vectors, but and yeah, this will be the first um, um, first 20 vectors that we will be using to display these images. In fact, we display the first three vectors as images by reshaping them to 50 by 50. And you can already imagine that for doing that, of course, the first thing, if the task that you need to do even before that is, of course, to load the images. This is similar to the MNIST case that we have already done, and you can already have a look at the way this data set has been arranged in the folder, and you can write a simple function to load them, just like we did in MNIST case. After that, the next task is to write a function that takes the input training set T, like the matrix composed of vectorized. Again, this training vectorized matrix, and we need to have, this will be the X, like X training X, and then we have need training Y, which will simply tell which person this image belongs to. So we have 10 classes, right? It is mentioned that we have, where is it? Yeah, so we have 10 subjects. So we have 10 classes. So the input training X is the vectorized matrix of the images, and the training Y is the vector of labels. And after that, the test samples are composed of vectorized pictures from subsets 1 to 4. So just like the training set, we will load the test subsets one by one, and also jointly. Okay, we will come to that again. But when you load test subsets and the corresponding labels, after that, what we do is we use SVD of both the training and the test subsets, and we use only the 20 singular vectors from the first step, like from this function. So we feed these training and test matrices to this function, which gives out the top 20 vectors, and based upon that we only based upon that we uh, based upon that we use these 20 singular vectors and find the Euclidean distance between the training and test sets to find out the best class that the sets belongs to. And for that, we use KNN approach with three nearest neighbors, right? So this is just like we already did in case of MNIST in the first in the lab or assignment. I don't remember now, but we already did that in case of MNIST. I guess we did that in lab, yeah. So yeah, so we use Euclidean distance of every test sample with all the training samples to find out, and then we find out the best three neighbors, and we average over their classes to find in which class this belongs to. So, and but remember, the whole purpose of this is to compare them in the reduced space, right? Right now, the images are like 50 by 50. We take them down in the and we pick only the top 20 singular vectors. Okay, please remember this. And afterwards, and then we see the error rate, the misclassification rate. We can simply see, like, if that Y test for a certain index was let's say 5, like the person index 5, and we gave person index 6. This means that the subtraction of these two vectors is not like at these two values is not 0. So we have an error. So I mean, you can implement it the way you want, but we count the number of errors and we divide them by the total number to find the error rate, and then we plot this error rate. Okay, and we repeat this for all the subset from 1 to 4, and we do this for k is equal to 1 to 20. Okay, so we plot the error rate for each subset, and I would recommend you to also plot the error rate for like joint for all the subsets together. Okay, please also see if we only use subset 0 for training and all the subsets for testing, then what happens. The second like the last task is we use the same thing, but here we remove the first three singular vectors. So we pick the vectors from let's say like number 4 to number 20. So like I.e. use k is equal to 1 to 17 starting from 4th. Like it means that like the index starts from 4 to 20. And plot the error rate as before, and then please explain what is the difference and how this error rate what happens to this error rate, and how do you justify that? So I guess this should be yeah, this is all. And if you have some question related to the assignment, maybe you can ask me right now. Otherwise, we can maybe close this. Okay, so I guess there is no question right now. So in that case, just let me see if there is something else I need to talk about. Yeah. So just one more thing. I mean, one last thing. I guess. Yeah, you just to emphasize once more. So we start with k is equal to one. Then for two, like for like top two vectors, and top three and four, and so on till k is equal to 20. Okay, and here we start with k is equal to 4 and go till k is equal to 20. So if you have some confusion, please don't hesitate to let me know. And the assignment deadline, you have enough time here. Like it is 12th of like it is 10th. Yeah, I'm sorry. So it is 7th of January. So about 1 month. Yeah. So that's all from my side, and I wish you guys all the best. And let's yeah, till next time. So goodbye.